Now we're going to look at how we can use Jupyter Notebooks and Python to do some simulations of the probability concepts we've been working on. So this is in the Probability Simulations Jupyter Notebook. And let's just start to head through this. So first, there's a great NumPy function, np.random.choice, that we can use to randomly select from a list or an array. So here, if I create this list that just consists of these letters, and I want to randomly select from this array, I can use np.random.choice, and then I put the list or the array in here, and it's just going to choose one element randomly from that list. So I could do it again, do it again, do it again. Now, it's treating all of these as equally likely because the way I've written the list is each element only shows up once. I could also choose a selecting more than just one. So I could say I want to select 4 times, but in each of these cases, this is assuming with replacement. So once I select, for example, E, it goes back into the list and is eligible to be selected again. So there's an example of selecting 4 items randomly with replacement. If you want to do replace false, then here I'm getting C and then I'm not putting it back in. Then I'm choosing A, I'm not putting it back in, then choosing B, then choosing D. So you notice I won't be able to do replace false on a size that's larger than the array itself. But here I selected D, and then when I selected E, my choices were actually only A, B, C, E, and F. Okay, so one way we can simulate coin tosses is just to create a list here with the 2 possible outcomes. And this is especially if I'm assuming that I have a fair coin. So I can have coin as the list, or I can also write it here. I'll do it as an array. Either way is going to work. And then when I do np.random.choice coin, again, it's going to choose randomly an H or a T with equal probability. I can simulate many flips of this coin by doing this. And then if I wanted to, for example, count the number of heads I get, then I can write out flips and then sum where flips is equal to heads. And so it tells me in this scenario, I had 2 heads. I can do it again. Now I have 6 heads. Do it again. I got 6 again. Here I have 3. Now, so far, this was assuming equally likely outcomes, but I can alter the probability with which np.randomChoice is selecting by adding in this p parameter here. And it's going to do it in the order. It'll match the order of this array that you give for your options. So because coin originally had heads first and then tails, this is going to assign heads 75% chance and tails 25% chance. And now we can see, all right, if I have a biased coin like that, I flip it 10 times. Here I got 5 heads, here I got 8 heads, here I got 6 heads. So notice I'm more likely to be getting more than just 50% heads with this biased coin. All right, so based on this, see if you can put this on pause for a minute and see how you would simulate rolling a 6-sided die. All right, so I'm going to make an array that gives me the outcomes. So 1, 2, 3, 4, 5, 6. And then I can do np.random.choice of the die. And there we go for one given roll. Let's actually just print it out so you can see. So that one got a 6, this one has a 1, this one has a 3, 1. I can do it many different times. Now, if I wanted to simulate rolling this 10 times, I can again say, excuse me, that's a different thing that I'm showing. Let's simulate rolling it 10 times. Well, then I would just add to my np.random.choice, I would put 10 here, and now I'm going to get 10 different rolls. If instead I had passed an int instead of a list or an array, so here I'm passing this int 5, then my random sample is generated as if it were from this automatic list. So let me show you. When I do np.arange 5, this is going to give me, not in a list, a NumPy array with element 0, 1, 2, 3, and 4. So that's what it's choosing from here when I'm running this. Sometimes it's helpful just depending on what you're trying to simulate. Okay, so we flipped a fair coin. Just so that we all get the same results in this next one, we're going to set what's called a seed, the seed method here. That's going to initialize the random number generator so that all of us start with the same seed value, so we'll get the same results here. Otherwise, we would get different results each time. So here I'm flipping a coin. This is a fair coin, it's flipping it 50 times. And now I would like to approximate my probability of heads by adding up the number of heads that I get. So again, I'm going to look for where were the flips equal to heads. That's going to give me a Boolean array here. And now I can sum. If I sum this, it's just going to count the trues as 1 and the falses as 0. And that'll give me the total number of heads. To get the probability, I'm then going to divide by the length. In this case, we know it was 50, but I'm just going to make it more generic. Okay, so here, and I purposely picked this random seed so that we got a strange probability. Even though this was a fair coin, sometimes you're only going to see 36% heads. That's the beauty of chance and randomness, right? And so this is far off from the actual probability of heads. But again, I only did 50 flips. So now I'm going to rerun the simulation using 500 flips. And we can see now, okay, now I'm getting much closer to the actual correct probability, which is 50%. So one thing we can look at is as we do more and more coin flips or increase our number of simulations, how does our estimated probability change? And in particular, we can plot it as a function of our number of flips. So before we do that, I'm just going to point out to you how the range function works because it's used in this loop here. So if I do for I or II in range 5, it's going to start at 0 and then count up for a total of 5 loops. So what I'm going to do in this code here is I'm going to flip my fair coin n times, and then I'm going to keep this running estimate of the probability as my number of trials gets larger. So I'm going to start at 0 and go up to my nth flip. But for example, suppose I got originally tails and then heads and then tails. So first it's going to, in the very first loop through this, it's going to say, oh, you got a tails. So that was 0 heads. So your probability of heads after 1 flip was 0 out of 1. Then after 2 flips, it's going to look and it said, okay, you got 1 head out of 2. So your probability of heads is 1/2. After 3 flips, we still had 1 head, now out of 3. So our running probability is now 1/3. And that's what I'm going to record now. I'm going to have an array that gives me the probability up to the nth entry, right, of how many heads have I flipped so far. And we're going to plot that just to get a sense of how this converges. So that's what's happening now. I'm going to run it for 10,000 coin flips. It's a lot. And then I'm going to plot my function here. I'm going to run plot estimates for 10,000 and output a plot. So this is doing plot P so that I can see how my estimates are changing. And I'm going to put the actual, I know what should be approaching the horizontal line of 1/2. So let's see. Aha, so now we can see what's happening. So it is going to bounce around slightly above, slightly below. If I run this again, you're going to get a slightly different bouncing, right? So same idea. But in general, I can see in the beginning, it's not so close to my exact correct probability. But the more I flip it, the closer and closer this will bounce back and forth around my probability of 50%. And that's what I get here. Here it's approximately 0.499. So this is useful because sometimes it's not going to be possible for us to theoretically do the calculations for a given probability, but we will be able to simulate it. And as long as we do enough simulations and let this go long enough, we should get very close to the theoretical probability because in the limit, the simulated probability approaches the theoretical value. Okay, so let's switch to drawing cards because this is also a common type of example that we've thought through in class. And so first let's do it theoretically. What is the probability of drawing 2 hearts from a standard 52 card deck? Okay, so let's think about it. Go ahead and try to do this theoretically first, and then we'll write a simulation for it. All right, there's multiple ways we can do this, but I always like to think, do I know what has to happen on the first draw? And I do. I know on the first draw, I have to get a heart. So I'm going to say first heart. And then the second draw, I also have to get a heart. And so using the multiplication rule, I want to know the probability of the first heart times the probability that the second is a heart, given that the first is a heart. And I can see, I'm going to write this using LaTeX just so we can see this. There are 13 hearts in my original deck out of a total of 52. So the probability the first one's a heart is 13 out of 52. And then the second one, well, now I only have 51 to choose from, and I've already chosen 1 heart. So now I only have 12 out of 51 options. And so when you simplify this, this ends up being 1 out of 17, which is approximately 0.0588. So that's our theoretical answer. Now let's write a simulation, and we're going to see if we do our simulation correctly, we should get very close to this actual theoretical answer. Okay, now let's build a deck. So we're going to simulate this to verify our results. So there's multiple ways you can do this. I'm just going to use list comprehension here, and let's just add the suit plus the rank so that I end up with a string. When I do that, here's one way you can represent your deck. All right, now let's write a function that's going to take a list, because what I want to do is see the probability of drawing 2 hearts. So first, let's take a list of 2 cards and return it true if they're both hearts. Otherwise, return false. So we can actually do this all in one step. If I imagine that I have my 2 cards, I'm going to check if the first card, so think of a list here, this is now looking at the very first card itself and then the first entry in the string. So that's the 0, 0 piece. I want to see if that's a heart. And then I can check again. Let's look at the second entry. We still want to look at the very first string, the first element in the string and the first letter. See if that's a heart. Okay, so that is now going to return true if they are both hearts. And we can just check here. So let's just do this assert statement, which is looking good. If you didn't even want to have the assert in here, you could just see what's going to happen. This one's going to spit out, oops, let's undo that. That one's going to spit out true, and then you can put in other ones, and I will see false. Okay, great. Now I want to draw 2 cards without replacement, and so there's 2 ways I can do this to simulate this. I can do np.random.choice cards replace false, size is 2, or there's also a built-in shuffle that will just randomly shuffle the items in a list, in which case I can do that and just grab the first 2 items. So here, just to see, I'm just shuffling and showing you this by grabbing the first 5. I'm going to print the deck as it is, randomly shuffle, and then pick the first 5 again, and you can see it's shuffled. So let's simulate a single draw of 2 cards without replacement and check if they are both hearts. So I'm doing np.random.shuffle. That's what I chose to use here. And let's just grab the first 2. So out of my deck, I'm just going to grab the first 2. And then check if they are hearts or not. And then, okay, the first 2, I didn't get both hearts there. Oh, the second 2 I did. So if we print this, you can actually see what's happening, right? Those are the first 2 I got. They weren't hearts. Second 2, they weren't hearts. So I'm going to keep doing this. And then eventually I might end up with 2 hearts. I was pretty lucky that first time around. All right, so we're going to now repeat this over and over and over. That's part of our simulation. Here we'll start by just doing 250. And we're going to say hearts is equal to np.array. Again, this is using list comprehension. So what I'm going to do is do that single draw, and I'm going to do it 250 times. So for, I can have my counter, I in range, and then choose what I want, num samples here. And then I can print, I probably should close this so we don't have to, or comment this out so we don't see all results. If I comment it out, so I got 0.064. And again, the true theoretical probability that we did above was 0.058. So I should do more simulations to get closer to that. Let's try doing, say, 500. Oh, there we go. I'm getting very close. And as I do more, we're going to get even closer. Now we're going to look at how we can simulate total probabilities. So the scenario in class that we did was drawing randomly from one of two boxes where there were different numbers of red balls in each box. And we wanted to know what's the probability I draw a red ball. One box was larger than the other, so we were more likely to draw a box out of box 1 to start than we were from box 2. And so that's what went into our calculation here in our total probability calculation. So how can we simulate this kind of two-step situation? There's definitely more than one way to do this. But what I like about Python dictionaries is they do allow us to consolidate when you have multiple pieces of information like this. So one thing we can do is use a dictionary to represent each box. And in particular, we're going to represent that we have green and red balls in box 1 with these different probabilities. And that's all represented in this first box 1 dictionary. Separately, I can say I also have box 2. It also has green and red balls with these probabilities. So I have 2 dictionaries now, each containing the information I need about my 2 boxes. Then I can put this all together, and I can now create one dictionary that says, okay, I have box 1 and box 2. So it's a dictionary of dictionaries, if you notice, right? The first entry here is actually a dictionary, box 1. There's another dictionary, box 2. And then it gives me the probabilities of getting box 1 versus box 2. So this is a useful way, again, not the only way by any means, but a useful way that Python can keep track of these nested situations. And I'm just going to print both of these so you can see what's happening. When I print, let's first just do box choices. So that's the overall dictionary here, and you can see that I have boxes and it's storing one whole dictionary there, another whole dictionary there, and then it's storing the arrays or the array of the probabilities of each of those boxes. In particular, I can call the label. So if I use my dictionary box choices and I call the label boxes, that's just going to spit out my 2 dictionaries. So let's do that here. Or I'm calling the key, excuse me. Boxes is the key in the dictionary here. And there you can see it's then outputting the value associated with boxes is 2 dictionaries. Okay, so given that, I'm just going to walk us through this next code just so you can start to see how we could simulate this idea. First, we're going to look at randomly sampling a single ball. That's what's happening in this def sample ball. So first, I have to randomly choose a box. And so I'm doing np.randomChoice, and I'm plugging in my 2 box choices here. So the box dict boxes, again, going to give me this here. And I have probabilities now of 2/3 versus 1/3. So it's going to randomly choose one of those 2 dictionaries, basically, with probability 2/3 or 1/3. That's what's stored in box. So if I were to print box out here, because we'll do this one time around just so you can see, it's going to give me one of those 2 dictionaries. Now, I'm going to randomly choose a ball from that box with the appropriate probabilities. So if I now call this once, sample ball, let's run this. And let's do this. Okay. There we go. So now I print it out. I happened to choose, let's see that was box 1. That's what I happened to choose. And then out of box 1, I happened to choose a red. All right, so I'm going to comment this because you're not going to normally need to see which box I choose. At the end of the day, I just want to see the ball. Okay. Now, what I'm doing manually here, I want to repeat in a function. So I'm just going to do this 1,000 times. Get a whole array here of the possible balls choices that I've gotten, and then count up the total number. In this case, I'm going to look at red because I want to look at the probability of getting red. So I'm going to count up the number that are red divided by the total number times I did this. I'm going to do this. I know I put 1,000 up here as the default. I'm just going to jump up to 50,000 here because it runs pretty quickly. And I can see 0.6621. That's very close to the actual theoretical value we derived above, which is 0.661. For this last example, let's look at how we can simulate conditional probabilities. So first, I want you to try this problem theoretically before we simulate it. So you're going to roll a die, fair die, twice. Let A be the event that the sum of the throws equals 4, and let B be the event that at least one of the throws is a 3. What is the probability that the sum of the throws equals 4 given that at least one of the throws is a 3? That is, compute the probability of A given B. Take a minute, put it on pause, and do that via paper and pencil. Okay, so here's my solution. I want this conditional probability. And I can look at, all right, my numerator, in order to get the probability of A and B. I'm going to get this so I can write here. Well, there's only 2 ways that I can get A and B, which is that the sum of the throws equals 4 and at least one of the throws is a 3. That happens 2 ways out of the total 36 things that I can get by throwing a fair die twice. So the probability of A and B, my numerator, is 1/18. Then I have to think about the denominator, the event that at least one of the throws is a 3. There's multiple ways you can think about this, but I'm going to think of, okay, let's suppose that event 1 is we roll a 3 on the first die. Event 2 is we roll a 3 on the second die. These are not disjoint. So I could say, what's the union? What's the probability of this or this? And that's going to be the probability that we roll one on the first plus the probability we roll one on the second minus the probability of their intersection. And so I can see here, probability that I roll one first, that I roll a 3 on the first die is 1/6. The probability I roll a 3 on the second die is 1/6. The probability that I get a 3 and then a 3, that's 1 out of 36 options here. And I'm writing it, in this case, as 1/6 times 1/6 because it is true these die rolls are independent. And so the joint probability, the probability of E1 and E2 does equal the probability of E1 times E2 because they're independent. So that gives me 11/36. That's my denominator. So at the end of the day, the actual probability is 2/11. Now we'll look at how we can simulate this. Okay, first, before we actually write code to simulate the conditional probability, let's just practice by reading through this code which simulates an estimate of the probability that if you roll a fair 6-sided die twice, the result will sum to 4. Okay, so first it's rolling it once, rolling it twice, and then it's saying, did it actually sum to 4? And then we're calculating the proportion of those results that did sum to 4. And that gives us an estimate here. And so I could say if I want to simulate this, for example, let's not print all this right now. I guess you're right. Let me print it once just so you can see what we were doing. Roll 1 is 2, roll 2 is 3. Did it sum to 4? No. Then I can do it. Let's do 10 so you can start to see. None of those were summing to 4. Maybe by now, there we go. We had one that did sum to 4. This one right there. So you can see then what's happening. 1 out of my 15 is what that percentage is there. Okay, now that's just to get you thinking how you might simulate this type of thing. But now I want you to modify this code so that we actually estimate the conditional probability. And NumPy has some nice methods, logical or and logical and, that may be potentially useful here. So try putting this on pause and see what you can come up with. Okay, so I'm going to start using the first 3 items that we had above because we need to roll this twice again. I'm not going to print it this time because otherwise we're going to end up with way too much info spit out here. Let's let this be size is num samples. Okay, so I've rolled it twice. Now what I want to see, my numerator needs to be, let's take both of the pieces in together. I want to look at A first of all. The sum of the throws equals 4. So let's call that data 1. Let's see whether or not that's true. Does roll 1 plus roll 2 equal 4? That's going to give me a Boolean output. Let's look at data 2, the other event I'm interested in, which is at least one of these are a 3. That's where I can use this NP logical OR, and it's going to look and tell me if either roll 1 is a 3 or if roll 2 is a 3. That's just a kind of quicker way of writing it. So these are both of my events, A and B. Now, if I want the conditional probability, then in the numerator, I want the probability of both, right? I want probability of A and B. So both, let's do np.logical and this is going to tell me where both A and B have been satisfied. Again, this is going to give me a Boolean array as my output. And now I'm close. Here's what I want to return. I would like the total number in both, so np.sum, total number of trues, np.sum both. Okay, that will be basically counting the number of ways that this occurred in the numerator, and then I'm going to divide by the number of ways it occurred, that event B occurred in the denominator. So what was my denominator? It's B, which was data 2. So I'm going to have np.sum data 2. So notice, yes, while the definition up here is probability over probability, if I can get counts, because my denominators are the same, let me show you what I'm really doing. I'm getting the counts here. So I'm getting the number of, let me put it this way. I'm getting the counts of this joint probability divided by my total number of simulations, number of sim. And then the denominator, I'm getting counts of when event B occurs out of my number of simulations. So notice the number of simulations there is going to cancel, and this ends up just being the count of when I have both events A and B satisfied divided by the counts of when I have B satisfied. And that's what I'm doing in the simulation. So let's run it. Aha, okay, and I got something close. Remember the actual answer was right around 0.18. I'm getting close. I can definitely do more simulations. Let's do that. There we go. And the more of these that I do, I'm going to get closer and closer. I did a lot there, so it's going to take a bit of time, but I'm going to get closer to the actual 0.181818. Yep, there you go. So that's a nice way to have some intuition around what we're doing when we're calculating theoretically, because we're now able to recreate this via simulation.